In this lecture today, we will look at Lamport timestamps or logical timestamps, one of the most important building blocks in cloud computing systems and any kind of distributed systems. So what we've seen so far is that synchronizing clocks across processes is a very hard problem. And the reason we are doing this is essentially because we want to order events across a distributed system, events that occur at different processes. So because clock synchronization is so challenging, why not just avoid doing clock synchronization and instead directly assign timestamps to events? For this, the idea used here is the idea of causality. So as long as the timestamps obey causality, assigning the timestamps to events might just work. This means causality means that if an event A causally happens before another event B, then the timestamp assigned to A is less than the timestamp assigned to B. What does causality mean? Causality means that one event leads to another. That is, there is a path of events from the first event to the second event. For instance, I can enter a house only after I unlock it. So the unlocking event happens before the entering of the house event. Similarly, you receive a letter only after I send it. So the sending event of the letter happens before the receiving event of that particular letter. So logical or Lamport ordering and timestamps were proposed by Leslie Lamport in the 1970s. Almost all distributed systems use it today, and all cloud computing systems, or almost all of them, use some form of logical ordering. If not Lamport timestamps, some variant of Lamport timestamps is used. So the logical or Lamport ordering defines a happens before ordering among pairs of events. Happens before is denoted as a forward or horizontal arrow. There are three rules that are used to determine whether or not two events are related by this happens before relationship. If the two events A and B are on the same process and the time at event A is less than the time at event B, notice that this is the time using that process's local clock, which only increases forward, which only moves forward. If time A is less than time B, then A happens before B. Okay, this is fairly common sense. This is like saying I open the house, I unlock the house, and then that event happens before me entering the house. Now, events might also happen at different processes. So if a process P1 sends a message M to process P2, then the sending of that message is an event. Similarly, the receiving of that message is an event. The sending of that message M is an event that occurs at P1, while the receiving of that message is an event that occurs at a different process, P2. But we say that the send of that message M, that event, happened before the receive of that event message M. Okay, this is like saying I send the letter and that happens before you receiving that letter. The third rule is transitivity, and essentially it says that if there are three events A, B, and C such that A happens before B and also B happens before C, then it's also true that A happens before C. And this allows us to relate very far away events to each other using the happens before relationship. The happens before relationship creates only a partial order among events. This means that only some pairs of events are related to each other via the happens before relationship. Not all events are. So for instance, if processes never exchange messages with each other, then all the events are essentially called as concurrent events. They are not related to each other at all across different processes. Events within a process are still related using the happens before, but across processes you do not have the happens before relationship at all. You'll see this notion of concurrent events coming out as we discuss the examples. Okay, so these are the three rules for for deciding when two events are logically related or causally related to each other. Let's see an example. Here's an example of three processes, P1, P2, P3. The time goes from left to right. Notice that the clocks may not be synchronized here at all. P1 executes a local step, which we label as an event A. Then it sends a message to P2. The send event is labeled as B. The receive event is labeled as F. P1 then executes another instruction C. It receives a message from P2. The receive event is labeled as D. And then it sends a message to P3, which is an event labeled as E. Okay, and similarly, P2 has a bunch of events, 3 events there, E, F, and G, and P3 has 3 events, H, I, and J. Okay, and a dot over here is an instruction or a step, and an arrow here shows a message. So Here is what the happens before might look like in this particular example. A clearly happens before B because these two are events at the same process P1 and the time at A is less than the time at B. Similarly, B happens before F because B is the send of a message and F is the receipt of that same message. And now using our transitivity rule, we can now say that because A happens before B and B happens before F, is also true that A happens before F. Okay, so essentially what we need is we need a path from one event to another in the causal space so that we can say that the first event occurred before the second event. Okay, so let's see some other examples of the happens before relationship. The event H, which is at P3 over here, happens before the event G, which is at P2. Why is this? Well, there is a causal path that goes from H to E to F to G, and therefore H happens before G. Similarly, the event F at P2 happens before the event J at P3. Why is this? Again, there is a causal path that goes from F to G to D at P1 to E to J at P3. Similarly, H happens before J because again there is a path that goes H, E, F, G, D, E, and J. And finally, C happens before J because again there's a path that goes from C, D, E to J. So you see several examples here of the happens before relationship being played out among pairs of events. So how do you assign timestamps, which is what we really wanted to do, right? So how do you assign these timestamps so that this causality that we said, the logical ordering, is actually obeyed? So there are a few rules that Lamport laid down to assign timestamps. Each process uses a local counter, which is an integer. We call this as the process clock. Okay? The clock is not the system clock, it's just an integer. The initial value of the counter is 0 at each process. Remember that this is a local counter, so each process is the only one that can access and update its counter. Now, a process, whenever it executes an instruction or sends a message, it increments its counter by 1. Okay? And it assigns this new timestamp to the instruction event or the send event of that message. When it sends a message, the send message also carries the timestamp that was assigned to the send event of that message. Okay, why is this carried with the message? This is used by the receiving process. When a process receives a message, it looks at the timestamp in the message, the send timestamp. It also looks at its local clock value. It takes the max of those and then it adds 1 to it, and it assigns this value as the timestamp of the receive event of that particular message. Why is this max operation done? Well, this is done because you want to make sure that if two events are causally related, they get timestamps, Lamport timestamps that obey that causality order, that the event that occurred later on in the causal space gets a higher timestamp value. Okay, so let's see this played out in action using our example. Okay, so this is the same example as we had before. I have removed the event names so that it's not cluttered. So initially, all the processes start with counters, clocks, which are initialized to 0. Then process P1 executes a step. It assigns it a timestamp of 1. It increments its local clock, assigns it its timestamp of 1. P3 at the same time sends a message. Again, it increments its local clock to 1. It assigns this as the send event timestamp, and the message also carries this timestamp value of 1. Now, when P2 receives this value, it looks at the message timestamp, which is 1, and its local clock, which is 0. Max of those is 1, plus 1 is 2, and this is assigned as the timestamp of the receive event of this particular message. Okay, this ensures that the send event, which happens before the receive event, are getting timestamps which obey the causality, and also any event that occurred before here at P2 would have a lower timestamp than the receive event of this message. Now, carrying this forward, next what happens is that P1 sends a message, which it does by incrementing its local clock from 1 to 2, assigns this as a timestamp to the send event of that message, and the message carries this timestamp. When P2 receives this message, it notices that its local clock is 2, the message timestamp is 2, and the max of those 2 is 2, plus 1 is 3, and that is assigned as the receive timestamp over here. Similarly, when P1 executes an instruction, it assigns it a timestamp of 3. When P2 sends a message to P1, it increments its local clock from 3 to 4, and sends 4 as the timestamp along the message. When P1 receives it, it takes max of 3,4, it adds 1, and that is 5, and that gives it the local clock value at its receive event. That's also the timestamp of the receive event. Notice that P1 jumps from 3 to 5, from going from one event to the next, and that's fine as long as the timestamp of this event 3 is less than the timestamp of the next event. We are obeying causality. Carrying this forward, P3 executes a local instruction which gets the timestamp of 2 because 1 is incremented by 1. When P1 sends a message to P3, it goes from a timestamp of 5 to 6. It includes this in the message. When P3 receives this, it looks at the timestamp in the message 6, which is more than the local clock value 2, and so 6 plus 1, 7 is assigned as a timestamp to the receive event of this particular message from P1 to P3. So that completes our example, but let's see a little bit how the timestamps are assigned to the events that we said were causally related. So earlier we said that A happens before B, and you notice that here they get timestamps that obey that ordering. So 1 is less than 2. B happens before F, we said earlier, and they get timestamps 2 and 3, which are ordered in that manner. 2 is less than 3. Similarly, A happens before F, we said earlier, because of the transitivity, and they are assigned timestamps 1 and 3 respectively, and 1 is less than 3, which obeys causality. We saw a few other causal relationships. H happens before G, and they get timestamps 1 and 4 respectively, and 1 is less than 4. Similarly, F and J get timestamps of 3 and 7, which obey causality. H and J get timestamps of 1 and 7, which obey causality, and C and J get timestamps of 3 and 7, which obey causality. However, there are some events which may not be causally related. So consider the two events C and F over here. There is really no causal path that goes from C to F, and also no causal path that goes from F to C. You can try to find a path, but if you go forward from C, you'll only go to P3 over here with J. If you go forward from F, again, you'll only go forward to J. There is no causal path that goes from C to F or from F to C. However, they get the same timestamps. These two events which have no causal path from one to the other are known as concurrent events. Consider these two events H and C, H over here at P3 and C at P1. They get timestamps 1 and 3 respectively. However, there is no causal path that goes from H to C or from C to H. And so these two events are also concurrent events. However, they got Lamport timestamps of 1 and 3 respectively at H and C, and this might seem to imply that these are causally related, but that's not necessarily true. So this means that if two events are causally related, then their Lamport timestamps obey the causality. However, if you get Lamport timestamps for two events, then that doesn't necessarily mean that the causality is in fact true in between those two events. So putting it another way, a pair of concurrent events doesn't have a causal path from one event to the other either way in the pair, and the Lamport timestamps are not guaranteed to be ordered or unequal for such pairs of concurrent events. They might be equal, they might be different, it doesn't really matter. But this is fine because these concurrent events are not causally related, so we are not violating causality by leaving this ordering up to the air. So essentially what I've been telling you over the last few slides is that if two events E1 and E2 are such that E1 happens before E2 using our logical ordering, then it's true that the timestamp, the Lamport timestamp assigned to E1 is strictly less than the Lamport timestamp assigned to E2. This is what I mean by saying that Lamport timestamps obey the causality. However, the reverse is not true. If I give you two events E1 and E2 so that the timestamp according to the Lamport timestamp of E1 is less than the Lamport timestamp of E2, this means that either E1 might happen before E2 or E1 and E2 might be concurrent. Okay? The only possibility that this is eliminating is that E2 happens before E1. That's definitely not true, but either of the other two possibilities may be the case over here. Okay, so the Lamport timestamps obey causality, but they don't always identify concurrent events. So in the next lecture, we'll see a way of assigning timestamps to events so that you can actually distinguish concurrent events from ones that are causally related.